In this talk, I will discuss adding pattern matching support to embedded domain-specific languages in Haskell. Embedded domain-specific languages, or EDSLs, form a powerful approach to solving problems within particular problem domains. However, it is often challenging to capture certain control constructs in EDSLs, as these control constructs are frequently not reified by the host language. An example of this being case expressions in Haskell. In this talk, we will present a technique for capturing pattern matching in a Haskell-hosted EDSL, and we will have a corresponding representation for algebraic data types, or ADTs. The fact that we are able to capture pattern matching by uniformly acting on ADTs using this representation is really the key idea of this work. This representation will support sum types, product types, as well as recursive types. We will also need to add lambda expressions to the deeply embedded EDSL in order to fully support the machinery behind the scenes necessary for capturing pattern matching using this particular method. We will also implement tail recursion in order to take full advantage of recursive types. So as I said, EDSLs are powerful tools. Applications include targeting accelerators such as FPGAs or GPUs, as well as 3D graphics description languages such as are used in virtual reality. And EDSLs can often use host language features, and in Haskell, a prominent example of this is usage of the type system, which is particularly, it's a static type system and it is a strong type system, so it allows many invariants that we care about preserving to be expressed within the type system, which is then checked at compile time. However, pattern matching is desirable to have in many EDSLs, but it is difficult to actually bring to use within an EDSL in Haskell. And this is largely because it is in part a control flow mechanism, and it is built into the Haskell language itself, and it is not exposed in a way that can actually be manipulated easily. So there's no direct way to capture it without accessing the abstract syntax tree, and we cannot really directly access the abstract syntax tree through normal techniques. Template Haskell is a possibility, but that brings its own challenges. And in order to address this, we will create a reusable representation for pattern matching using a GHC core plugin, and this GHC core plugin will access the abstract syntax tree of the EDSL code. This representation allows normal Haskell code to look at pattern matches that are given within the EDSL. So looking at the Haskell code in this slide, we see that example has a pattern match on x, which is an either of char and int. And we see that it is as a whole, example has type e of int. And e is the expression type for our EDSL language. So externalize brings a value from the host language, in this case Haskell, into the EDSL language. And this value, in this case, depends on this pattern match on x. And we want to actually capture this pattern match so that we can actually examine the pattern match within the EDSL and look at the structure of the pattern match and potentially translate it to something else. So, as I said, internalize brings a Haskell expression into the EDSL, and internalize goes the other direction. And we can see that externalize has this type, as shown in the slide, where there is maybe some constraint, and then it has type A to E of A. But how can externalize work? Well, externalize cannot be implemented as a Haskell function due to the issues I mentioned earlier. It has to operate on an abstract syntax tree. So the actual implementation is given by the core plugin. And it's also worth mentioning that a call to externalize so to speak. It's not an actual function, but a call to externalize, captures the surrounding function definition so that the function arguments can be handled properly, and this is necessary for the tail recursion transformation, which will be described in more detail a little bit later. Now, before we get to the implementation of externalize, we need to think about the expression type E and how might we be able to structure this type so that we can properly represent pattern matching. And before we even get to that, we need to think about how can we represent algebraic data types in a uniform manner. An important observation to make is that algebraic data types are constructed out of other algebraic data types in two main ways, as sum types and as product types. And overall, an algebraic data type is a sum of products. So, considering this fact, we can abstract away details of any particular ADT, or algebraic data type, which would be the constructor names in particular. And these sum of product structures can be examined directly without these names kind of being present. And this representation where the names are abstracted away and it's a uniform representation of the actual sum of product structure is what we call the canonical type for the ADT. And now that we're able to do this, we only really need to think of things in terms of these canonical types. The type family eRepti gives the canonical type of a given type, and the instances for eRepti can be automatically derived for any type that is an instance of generic. Now, to give an example, consider this complex pair type which has two complex doubles as its fields. If we apply the eRepti type family to it, we see that we get a pair of complex double and complex double. Now, it is worth noting that we did not actually deconstruct this fully. Complex double is itself a pair of doubles, and we didn't fully go down into this structure when we, in the result of eRepti. eRepti did not fully descend into the structure. And this is actually a key feature that is important for implementing recursive types, as we will discuss later on. So canonical types, as I said, will turn any sum type into an either and any product type into a pair. And really the key idea of the whole thing here is that by operating on canonical types, so when we talk about representing pattern matching a little bit later, we only have to talk about doing it on these canonical types, and we don't have to worry about the specifics of certain ADTs. We can just convert it to its canonical type representation and work on that canonical type, which is something that we can do without knowledge of specific things, specific information about certain ADTs, such as constructor names and so on. So eRepti is a type family that's associated to a type class, and that type class represents all the types that can be used within the EDSL, and this type class is eRep. Now that we have these two constructs, eRep and eRepti, we can start to define the data constructors of the E-type. Now for the moment, we're going to set the first one aside. This is the construct rep, and we will note that the remaining constructors are all pretty standard data constructors for introducing ithers and pairs, that is sum types and product types, into a embedded domain-specific language. We have a data constructor that brings in left values of the left type of a sum type and of the right type of a sum type, and we also have a data constructor that takes in two EDSL expression language types and gives you back a pair within the expression language. Now that constructor at the very top, construct rep, it is used as part of the transformation from the host language into the EDSL. And it transforms a value that is in its canonical type to a more specific type. So using the example from earlier of complex pair, the canonical type was a pair of doubles, or a pair of complex doubles, and the original type was complex pair. So constructor up takes a E of that canonical type, and it gives you back a E of complex pair. And this is how complex pairs, for example, are introduced into the EDSL. So now we can turn our attention to representing pattern matching, now that we've looked at how ADTs are represented. So a pattern match is represented using this case exp data constructor in the E type. And there's a constraint in this type, but we will ignore that. It's not too relevant for this talk. And we will see that there are two fields. The first field is the scrutiny of the match, which is the thing that is being matched on. In Haskell, it would be the thing between case and of. And the second field is something that represents the list of match alternatives. And this uses a sum match type, which will be discussed in more detail shortly. So the sum match type represents essentially a function, well, E of sum match repti t and r, as shown in the slide, represents a function in the EDSL from E repti of t to r. It is essentially a function which matches on the possible alternatives of that sum type. And more specifically, it is a list of E prod match values, one for each possible alternative in the sum type. So within each branch of the sum type, we're matching on the product. Since remember, ADTs are sums of products, we have a list of matches on a match on the sums, which is expressed as a list of matches on products. And we can see here that the data constructor is corresponding to the introduction of this sum match, which I've highlighted, is corresponds to something kind of like const for a list. There's the case for the empty list where there's no alternatives or no remaining alternatives in the pattern match. And there is a special case for when there is only a single alternative. And we can see that in sum match expression, the first one that's kind of like const, it kind of destructures an either into something that matches on a product in the left of the either and another sum match on the rest of the either. So now we look at product matches. So product matches can also be thought of somewhat as a list. They're a little bit less like a list than sum match, but they're very much like a function. And in fact, they have a EDSL function. Generally speaking, they have an EDSL function inside of them. And this conceptually operates on one of the elements of a pair, and then it gives you back a function which deals with the second element of the pair. And this could be a nested pair of pairs, and so forth. And so that function gives back another prod match, and we can see that in this first constructor here. And again, we have a special case for when there is a single match, and when there are no more elements of a pair to match on. So as I said, in effect, it is somewhat like a function. E of prod match S of t and t is somewhat like a function from S to t. And in fact, internally, it is represented as a function. And when it's being translated into its reference semantics, and likewise for sum match. And we can see that currying kind of is represented at the very bottom of the slide, except that the expression types kind of are interleaved there. So as we saw, we needed a function inside the expression language, so we need some kind of representation of lambda or something like that of lambdas. And the way that this is done is using globally unique names, the Behrend-Rett convention. And it is also worth mentioning that when things like pattern matching and tail recursion are captured, when control flow is captured already in a deeply embedded domain-specific language, it is quite a bit easier to also capture lambdas, because then when you're doing something like passing in, like if you apply the lambda to a var with a fresh name, it doesn't encounter any control flow that will disrupt the var from being pushed all the way through the lambda. And typed names are also used internally, and those are just a wrapper around ints. So summatch and prodmatch are primarily type tags that are used in the GADT representing the expression language, but also, as I alluded to earlier, the reference semantics uses the fact that they wrap functions. So returning to our original example, we see that example gets translated by the core plugin into example prime, and we can see all of the constructor, or many of the constructors that we've talked about in action, so to speak, and I've highlighted the right-hand side of each branch in the generated deeply embedded case match. And here we see more details of the actual plugin transformation. There's quite a bit more involved, which you can see in the paper, but many of the most pertinent rewrite rules are given here. We can see that the rewrite rule for case expressions will introduce this case exp, and we can see that the list of branches, this B rule gets recursively applied to those and introduces some match expressions, and then P for product matches, which introduces these lambdas, which this A introduces lambda, and M marks a sub-expression for further transformation, and that's outside the scope of the talk, but you can see it in the paper. And as I mentioned before, there is something that recovers the reference semantics, and this is done by abs, which is more or less has type E of T to T. And this function uses helper functions, prominently summatch abs and prodmatch abs, which respectively give the reference semantics for matching on some types and on product types. And here we can quickly see that the action of prodmatch abs on prodmatch values utilizes the fact that prodmatch values are actually function wrappers, or wrap functions, and we can see how this is used in this excerpt from the implementation here for the reference semantics. As I mentioned earlier, erepti does not descend fully into types. It only goes into the first layer of types, and this allows recursive types to be implemented in a relatively straightforward manner. Consider the intlist type as given in the slide. If we were to think about erepti applied to intlist, if erepti descended fully into the type it was given and completely destructured it, then that would be a non-terminating type level computation, because it would never stop going into the recursive, the recursion of it. And it only actually goes into the first layer. So the type equality shown near the bottom of the slide holds, which shows erepti of intlist is the same as either of unit and a pair int in intlist. And this is, we're able to do this due to the fact that whenever a pattern match occurs inside core, it only matches on sort of the first layer of structure. So at each pattern match, we only need to deconstruct the first layer. We only need to destructure that first layer. So we can kind of do this as we go along instead of all at once. Here's a simple example of this int list in action and the externalize and internalize functions being applied to it. And the core plugin will turn this into an appropriate an appropriately translated case expression, even though it is on this recursive type int list. This terminates correctly and exhibits the behavior that you would expect it to. Notice also that this is an example of why externalize and internalize need to capture the function surrounding it, the function definition surrounding it, so that the arguments are handled properly. In this case, t is a free variable within the externalize, the argument to externalize, so this needs to be handled properly, and this is discussed in more detail in the paper. Now, tail recursion is useful for many reasons, but once you have recursive types, it is often useful to have some form of recursion, such as tail recursion, in order to make better use of them. And we encode tail recursion in this particular way shown in the slide, where we eliminate the actual recursion and turn it into a function that can be stepped over and over, and the equivalence to tail recursion is one direction of it is witnessed by the code given at the end of the slide. And this allows us to have this deep embedding of tail recursion as shown in the slide, where we have step and done, and then this sort of tail rec embedding that actually holds the function that represents a tail recursive function. And we see at the bottom of the slide an example of a tail recursive function operating on an int list. To conclude, pattern matching can be represented in a reusable fashion in a Haskell-based embedded domain-specific language. Note that we did not use any specific details of a particular problem domain. And this representation can be captured using a GHC core plugin. Now, this was made possible by a uniform representation of ADTs, that is their canonical type, and this canonical type establishes a scaffolding or infrastructure on which to build a pattern matching representation such as described in this talk and in the paper. Now, also it was noted that lambdas become easier to capture once control flow constructs, including pattern matching as well as tail recursion, are already captured, as you can do that technique of sort of pushing that var constructor through the lambda without it hitting a control flow, a conditional, essentially, such as a pattern match or something along those lines. Future work includes looking at more applications for this system and more examples of this in action, as well as a more in-depth comparison to template Haskell-based approaches for expanding the expressibility of embedded domain-specific languages in Haskell, and sort of a more in-depth contrast and a examination of the pros and cons of each approach. Thank you for your time.